We've all seen large language models nail stance detection on straightforward examples. But ask them to judge the stance toward a political target in a heavily implied, context-dependent tweet, and performance doesn't just gradually drop. It collapses in a very specific, predictable way. And here's the kicker. Throwing chain-of-thought reasoning, retrieval-augmented generation, or even multi-agent debate at the problem doesn't fix it. Today, we're breaking down a new framework called SICI, which reveals that LLMs don't just get harder examples wrong. They undergo a regime shift in how they fail. To understand why, we need to stop treating all stance examples as equally hard. Stance detection asks whether a text expresses favor, opposition, or neutrality toward a specific target. The standard assumption in prompt-based LLM research is that if the model already knows the relevant language and world knowledge, then clearer instructions, explicit reasoning, or external context should elicit better judgments. But the empirical picture for hard examples tells a different story. The researchers introduce SICI, the Stance Inference Complexity Index, to measure exactly what makes a target text pair difficult. Instead of relying on surface proxies like text length, negation density, or lexical diversity, SICI quantifies the semantic and pragmatic burden across 7 dimensions: target visibility, scope alignment, pragmatic implicitness, knowledge requirement, context dependency, label ambiguity, and the polarity stance gap. Each dimension is scored from 0 to 4, where 0 means the inference step is trivial, and 4 means it requires heavy pragmatic bridging or external knowledge. The index itself is calculated as a weighted combination of the mean and maximum dimension scores. The mean captures the cumulative inference load, while the maximum captures a single severe bottleneck that can derail the entire prediction. The scoring protocol is deliberately separated from stance prediction to avoid circularity, and validation across 3 independent LLM scorers shows substantial agreement with a Krippendorff's alpha of 0.771. So what happens when you map LLM accuracy against SICI? You don't get a smooth, linear decline. You get a phase transition. The data reveals 3 distinct regimes. In the low-complexity region, models are actually quite accurate, but they exhibit a strong bias toward overattribution, specifically predicting against even when the gold label is neutral or favorable. Then, around a first breakpoint at a SICI score of roughly 0.45, accuracy hits a trough. This is the unstable boundary region. Finally, once complexity crosses 0.7, the model's behavior flips entirely. Predictions rapidly concentrate on none. This isn't just a drop in accuracy, it's a qualitative shift in decision strategy. Piecewise regression confirms this structure fits the data significantly better than a linear model, with a 70% reduction in residual error. The model isn't just uncertain. It falls back on different heuristics in different regions. First, a tendency to treat social media text as opposition, then a tendency to abstain with none when the target text relation becomes indirect. You might expect that scaling up the model would flatten this curve. But the research shows that stronger models like GPT-4o don't eliminate the regime shift. They just move the boundaries. GPT-4o successfully reduces the low complexity against fixation and pushes the high complexity abstention threshold higher. Yet the correlation between SICI and accuracy remains negative, and the high complexity region is still dominated by non-escape. This tells us that the bottleneck isn't a lack of raw capability. It's a fundamental limitation in how these models handle underdetermined pragmatic links. This regime structure also exposes a critical flaw in how we interpret the none label. When the researchers cross-validated across SEM-eval and VAST, they found that high SICI none predictions aren't semantically uniform. In SEM-eval, many high-complexity cases are actually implicit against stances that the model incorrectly maps to none. In VAST, high SICI examples are genuinely underspecified, making abstention the correct call. SICI cleanly separates failed inference fixation from information insufficient abstention. And when the authors tested 15 inference time interventions on the high-complexity subset, the results were stark. Zero-shot and self-consistency still tied for best. Chain of thought, counterfactual reasoning, Wikipedia RAG, and even multi-agent debate either underperformed or actively harmed accuracy. The interventions don't break the bottleneck. They just swing the model along an attribution abstention pendulum. Prompts that encourage indirect reasoning reduce against errors, but overshoot into excessive none predictions. Debate-style prompts can hallucinate stances or overcorrect in the opposite direction. The hard cases often require contextual or pragmatic information that isn't recoverable from the visible text target pair. Even when retrieval helps, it only marginally improves scores because generic encyclopedic knowledge doesn't supply the conversational or discourse-level context these examples actually need. So what does this mean for evaluating and building stance systems? First, SICI proves that instance difficulty should be measured structurally, not just through surface features or model uncertainty. Second, it suggests that benchmarks need to report their complexity distributions. A dataset dominated by low SICI examples tests direct target matching, while one heavy on high SICI non-none cases tests pragmatic inference and abstention calibration. Without that stratification, cross-dataset comparisons are fundamentally apples to oranges. For practitioners, SICI can serve as a triage signal. Low-complexity predictions can be used directly. Intermediate cases need calibration checks. And high-complexity cases should trigger abstention, targeted context retrieval, or human review, rather than forcing a decisive label. The era of throwing more reasoning steps or external knowledge at every ambiguous example is hitting a ceiling. The future of stance detection lies in complexity-aware evaluation, calibrated abstention policies, and systems that recognize when the target text link simply isn't there to be inferred. If you want to dive deeper into the 7-dimensional rubric, the segmented regression methodology, or the full intervention suite, I've linked the original paper in the description.